everyone, this is a run through the mechanics questions that are part of the A-Level Physics Year 1 workbook. The suggestion is that you've got a copy of this workbook printed out, that you've had a go at the mechanics questions before watching this video, and then this video can be helpful in giving you some explanation as to how to do the questions, particularly the ones that you found harder. So let's start with question 1 on the mechanics questions. Right, here we are. So question 1A, state what is meant by a vector quantity, so quantity with both magnitude and direction. 1 mark. Give one example of a vector quantity, so any from those listed there. Displacement, velocity, acceleration, force, momentum. Question 2. So this is a vector question where we have to draw a scale diagram. So you're given the size, the magnitude of the two vectors and the directions as well. So we've got a canoeist moving at 3.8 meters per second to the right, shown by the arrow. And there is a second vector, which is the current of the water, which has a velocity of 1.5 meters per second at 30 degrees to her original direction of travel, as shown here. So we need to use a ruler. We need to draw a scale diagram. If you did that and used a sensible scale, such as 1 centimeter equals 1 meter per second, that will be 1 mark. If you constructed the diagram adding the two vectors together, this is only a sketch of it, you'd need to do it properly with a ruler. You've constructed a diagram where both vectors are drawn to scale, and you use a protractor to measure the angle here, 30 degrees, and you've then drawn in the resultant. That would be the second mark, and the third mark is for the value, actually measuring the length of that resultant using the same scale, measuring and writing down what that value would be. So 2.6 meters per second. There's a range here of plus or minus 0.2, so values between 2.4 and 2.8 would be accepted. Question 3. This is a paracenter being towed at constant velocity. We're given the free body force diagram showing the forces acting and the angles at which they act. So we know that the sum of the vertical forces equals 0. In fact, it's going at constant velocity, so the sum of all the forces, there's no resultant force acting. So the vertical forces must combine to equal 0. That's going to help us to find the weight of the paracenter. So we're given some values, we're given the drag and we're given the tension. That's going to be helpful. So the first thing to do is to resolve the components. So we've got a vertical component of this tension here, which is T sine 27, or 2.2 times 10 to the 3 times sine 27. And we've got a vertical component of the drag, which is D sine 41, which is 2.6 times 10 to the 3 times sine 41. So if you found either of those vertical components correctly, then that's 1 mark. To actually solve this, we need to combine the forces together. So the weight plus T sine 27, that's our total down, is going to be equal to D sine 41, which is our upwards force. W, the weight, equals D sine 41 minus T sine 27. Put the values in and calculate the final value, 706.97 or 710 newtons to 2 sig fig. So second mark for a correct expression such as this one, or for substituting values incorrectly, and the third mark is for the final value. Right, on to question 4, which is the moments question using this lever system, which Archimedes is said to have used, something similar to this. So just get an idea of what's going on. So if you pull on this, the idea was that they pulled on this rope here, that pulled this lever down, which then pulled up on this end, and that would have lifted the ship at this end. So it's a moments question because we're going to be pivoting, well, to start with, pivoting around this point, but we've also got pivot points at here. So the first part of the question, A part 1, calculate the mass of the ship if its weight was 3.4 times 10 to the 4 newtons. This is just a case of using W equals m times g. We don't have to do anything with moments here. So mass equals weight divided by gravitational field strength, which is 3.4 times 10 to the 4 newtons divided by 9.81, which is 3466, or 3,500 kilograms. It's a 2 sig fig. Part 2, calculate the moment of the ship's weight about point P. State an appropriate unit for your answer. So we have got the weight acting, pulling down from the centre of gravity here, and we've got the pivot point at point P. So that's going to give us a moment. Moment equals force times perpendicular distance. So we've got the weight, 3.4 times 10 to the 4 newtons times 5.0 metres, equals 170,000. And the unit is Newton metres. You can write 170,000 as 1.7 times 10 to the 5. Calculate the minimum vertical force T required to start to raise the front of the ship. Assume the ship pivots about point P. So looking at the diagram, we've just calculated the clockwise moment. We now need to balance that. So the anti-clockwise moment will equal the clockwise moment. So T times 12 will equal 170,000, which we've just calculated here as our clockwise moment. So T times 12 equals 170,000. T equals 170,000 divided by 12, which equals 14167 newtons, or 14,000 newtons. So a mark for your substitution of the values and a mark for the final answer. Part 4, calculate the minimum force F that must be exerted to start to raise the front of the ship. So looking at the diagram, the tension force here is not perpendicular to the pivot, which is here. The axis of the pivot is going to be there. The tension of the force is going to be down there. So we are going to consider this as a vector triangle where the tension that we are going to have to apply, if you like, is T dash, which is bigger than T, because T is actually a component of T dash. So T equals T dash cos theta. That gives us our value of T lower than T dash. So T dash equals T divided by cos theta, which is 14,000 divided by cos 24 degrees, which is 15,325. So we've now got a value of the component, or not the component, the force of tension, which is perpendicular to the pivot. And the force that will actually be applied to the rope is going to be less than that because it's a component of it. We can then take moments with this lever system. So F, which we need to find, times 8 clockwise moments is equal to T dash times 2.5. We just calculated T dash. So F times 8 equals 15,325 times 2.5. And from that we can find F, which is 4,789 newtons, or 4,800 newtons. There's an alternative approach to this question which can be read in the mark scheme, but I think this is the most logical to follow method. Okay, moving on to question 5. A car of mass 1,300 kilograms is stopped by a constant horizontal braking force of 6.2 kilonewtons. Show that the deceleration of the car is about 5 meters per second. So here we're going to use F equals m times a, force equals mass times acceleration, just rearranging that to get acceleration. A equals F over m. So it's 6.2 times 10 to the 3 divided by 1300 equals 4.77, and that is about 5 meters per second squared. So remember, in show that questions, you need to do a calculation and arrive at a value. You then compare that value with the value that's given. Part B, initial speed given as 27 meters per second. Calculate the distance travelled by the car as it decelerates to rest. So it is going to be a Suvat equation, but which one? So we're given U, 27, V will be 0, at rest the final velocity will be 0. A equals minus 4.77, just calculated that, and we were asked to find S. So an equation with U, V, A and S in it. V squared equals U squared plus 2AS would be suitable. So rearrange and substitute. S equals V squared minus U squared in brackets over 2A. Put the values in. We should get 76.4 meters. So the marks are for selecting the correct equation, for substituting in the values, and for the final answer of 76 meters. Question 6. A supertanker of mass 4.0 times 10 to the 8 kilograms, cruising at initial speed of 4.5 meters per second, takes 1 hour to come to rest. Assuming the force slowing the tanker down is constant, calculate the deceleration of the tanker. First thing to say, if it's constant acceleration, which we call uniform acceleration, then that means that that we can use Suvat equations. So we're told the force is constant, so the acceleration must be constant, and so therefore we can use Suvat's equations of motion. So deceleration of the tanker, we're given U. We know U is 4.5, that's the initial velocity. V will be 0 if it comes to rest. T in seconds will be 3,600 seconds, so it's just taking 1 hour, multiplying it by 60 and by 60 again. So V equals U plus AT, substitute in the values. That's the first mark. 0 equals 4.5 plus minus 3,600 times A, because A is negative. That gives us A equals minus 4.5 divided by 3,600, which is 1.25 times 10 to the minus 3, which should be a negative value, but you're not penalised here if you don't include the negative. So mark for substitution, mark for final value. Part 2, the distance travelled by the tanker while slowing to a stop. So again, selecting the correct Suvat equation. S we need, so that needs to be in the equation. V equals 0, U equals 4.5, A equals 1.25 times 10 to the minus 3, and T equals 3,600 seconds. So you can use S equals V plus U over 2 times T. So that will be 0 plus 4.5 divided by 2 times 3,600 equals 8,100 meters. Or you could use V squared equals U squared plus 2AS, and you should arrive at the same value for the distance. So 1 mark for substituting values into a correct Suvat equation, and the second mark is for the final value. Part B, sketch on the axis below a distance time graph representing the motion of the tanker until it stops. So it's got to be a line that's curving over like that, and for the second mark, that's 1 mark. For the second mark, it's got to start at 0, 0, and it's got to end with a horizontal gradient. The line has to go horizontal here. So to explain that graph, part C. The gradient of the graph represents the speed, and hence the graph has a decreasing gradient. The ship is slowing down. Part 7, this is the motion of a long jumper, which is similar to that of a projectile. So we can be thinking about using our knowledge of projectile motion here, and equations of motion. So during this part of the jump, the centre of the mass of the athlete falls 1.2 meters. Calculate the time between positions A and B. So we've got a distance of 1.2. We know that we can use S equals half gt squared for motion where the initial vertical velocity is 0. So the ut part of S equals ut plus half at squared equals 0. So the equation then becomes S equals half at squared. A is g, which is the acceleration of free fall. So the equation becomes S equals half gt squared. And then rearranging that to get time, we get t equals the square root of 2s over g. So it's 2 times 1.2 divided by 9.81, which is equal to 0.4946 or 0.49 seconds. So 1 mark for substituting in the correct values into this equation, and the second mark for the final value. 0.5 is okay because that's just one sig fig, but not 0.50 because that's actually incorrect to 2 significant figures. Part 2. The athlete is moving horizontally at A with a velocity of 8.5 meters per second. Assume there is no air resistance. Calculate the horizontal displacement of the centre of mass from A to B. So S equals ut plus half at squared becomes S equals ut for the horizontal components. So we assume the horizontal velocity is constant. The clue there is there's no air resistance, and therefore there's nothing to slow the motion down horizontally. So 8.5 meters per second will be maintained. So S equals ut equals 8.5 times 0.49, which is 4.165 or 4.2 meters to 2 significant figures. 1 mark for substituting in the correct values and 1 mark for the final answer. B part 1. The athlete in the image slides horizontally through the sand a distance of 0.35 meters before stopping. Calculate the time taken for the athlete to stop. Assume the horizontal component of the resistive force from the sand is constant. So again, that means we've got a constant force acting, which means the acceleration will be uniform, which means we can use the Suvat equations. So what are we given? We're given S, 0.35 meters. U, we know, is 8.5 meters per second from the previous question. Here. V will be 0, final velocity will be a 0, and time we are asked to calculate. So from that we can select a Suvat equation, which has got S, U, V, and T in it. So the one here that I've used is S equals V plus U over 2 times T. So 0.35 equals bracket 0 plus 8.5 over 2 times T. And that then gives us a value of 0.80824 for T, which is two significant figures. So 1 mark for substituting in the correct values to the equation and 1 mark for your final answer. B part 2. The athlete has a mass of 75 kilograms. Calculate the horizontal component of the resistive force from the sand. So we're going to find acceleration using Suvat, and then we're going to find the force from F equals m times A. So we are given the mass here. So A equals V minus U over T, 0 minus 8.5, O divided by 0.082. And then multiplying that value by 75 to get the force. So it's F equals m times A, and that is 7774.3 newtons, or 7,800 newtons to 2 sig fig. We could instead use loss of kinetic energy equals force times displacement. which is the work done. And that would give you a value of 7741, which also rounds to 7,800 newtons to 2 sig fig. So that would get you the marks as well. 3 marks for this one. One is for finding the acceleration, one is for substituting into F equals m times a, and one is for the final value. For question 8, figure 1 shows a skier being pulled by a rope up a hill with an incline of 12 degrees at a steady speed. We're given the mass of the skier is 85 kilograms. Two of the forces acting on the skier are already shown. A, mark with arrows and label a further 2 forces that are acting on the skier. So we've got the weight acting down from a centre of gravity, and we've got a frictional force. So you could also have air resistance from the body pointing backwards, but most likely it's going to be friction from the skis acting backwards. The weight arrow must be vertically down from somewhere on the skier's body. Okay, so that's 2 marks, 1 mark for each correctly drawn force arrow. Part B, calculate the magnitude of the normal reaction on the skier. Gravitational field strength given as 9.8. The first thing is to find the weight. W equals m times g, so it's 85 times 9.8 equals 833 newtons. And then we're going to find the normal reaction force is going to be equal to W dash, which is a component of the weight, if you see my little diagram here. So the skier is pushing down on the ground with a force W dash, and the ground is pushing back up with a force R from Newton's third law. So R equals W dash, which equals W cos theta, which is equal to 833 times cos 12. Just recognising the angle is 12 degrees there. So it's this angle here between W and W dash. It's 12 degrees. It's the same as the incline of the slope here. It's going to give us a value of 814.8 newtons, or 810 newtons to 2 sig fig. So 1 mark if you have attempted to find a component of W of the weight and not the mass. Second mark for a correct substitution calculation, and third mark is for the final value stated with the unit. C, explain why the resultant force on the skier must be 0. So if they're moving at a steady speed or moving with 0 acceleration, or a resultant force other than 0 would change their speed. So it's just one of those statements needed, just 1 mark for that question. So that question is 6 marks in total. Question 9. The world record for a high dive into deep water is 54 metres. Calculate the loss in gravitational potential energy of a diver of mass 65 kilograms falling through 54 metres. So we're going to use change in gravitational potential energy equals mg delta h. Mass times gravitational field strength times the change in the height. So that's going to be 65 times 9.81 times 54 metres, and that gives us 34,433, or 34,000 joules to 2 sig fig. Part B, calculate the vertical velocity of the diver the instant before he enters the water. Ignore the effects of air resistance. So if we're ignoring air resistance, then we assume all of the gravitational potential energy is converted to kinetic energy. So 34,433 joules equals a half times m times v squared. half times 65 times v squared. Rearrange and calculate b. b equals the square root of 2 times 34,433 divided by 65, which equals 32.55 or 33 meters per second to 2 sig figs. We can use a suvat such as v squared equals 2gs to arrive at the same answer. That would get you the marks. So 1 mark is for this first expression, using the idea that the loss in GPE is equal to the gain in kinetic energy, and the second mark is for the final value. Part C, calculate the time taken for the diver to fall 54 meters. Ignore the effects of air resistance. So it's using S equals half gt squared again, where we want to know t. So t equals the root 2s over g, 2 times 54 divided by 9.81 equals 3.32, or 3.3 seconds to 2 sig fig. Values between 3.2 and 3.4 are accepted. Part D, explain with reference to energy why the velocity of the diver is independent of his mass if air resistance is insignificant. So we assume all of the gravitational potential energy converts to kinetic energy. None of the gravitational potential energy converts to thermal, and we can show that the masses cancel in the equation mgh equals half mv squared, as shown here. So this is 3 marks. So 1 mark for assume all potential energy converts to kinetic, 1 mark for no potential energy converts to thermal, and the 3rd mark is for saying the masses cancel, or for writing this out and showing with dashes through the m's that they cancel. Question 10, which is the roller coaster car, which is accelerated from rest to a speed of 56 meters per second along the horizontal track. Before ascending the steep part of the track, the roller coaster becomes stationary at C, the highest point. The total mass of the car and the passengers is 8,300 kilograms. Part A. The angle of the track is 25 degrees, the horizontal. Calculate the components of the weight of the car and passengers along the slope. So there's going to be a component of the weight here which acts back down the slope, which will tend to pull it back down the slope. So the first thing is to calculate the weight. W equals mg, is 8,300 times 9.81 equals 81423 newtons. And then we're going to find W slope, the component of the weight down the slope, from W sine 25. So it's 81,423 times sine 25 degrees, and that's 34,410.8 or 34,000 newtons to 2 sig fig. So this little diagram may help with that. Got the weight acting vertically down. We're finding this component with the red arrow here. So it's a component of the weight which is pulling back down the slope. This angle here between weight and W slope isn't 25 degrees. So therefore we're going to use sine of 25. We could also use cos of this angle, which is 65. Think about it as a right angle triangle. B part 1, calculate the kinetic energy of the car, including the passengers, when travelling at 56 meters per second. So it's a case of using the equation half mv squared. So half times 8,300 times 56 squared, 1 mark, equals 1.3 times 10 to the 7 joules for the second mark. B part 2, calculate the maximum height above A that would be reached by the car and the passengers if all the kinetic energy could be transferred to gravitational potential energy. So we're saying that all of that kinetic energy, 1.3 times 10 to the 7, is going to be transferred to GPE, so that is equal to mg delta h. And we can then put the values in for m and g, and then we can find delta h. So it's 1.3 times 10 to the 7 divided by 8,300 times 9.81 in brackets equals 159.8 meters, or 160 meters to 2 sig fig. Part C. The car does not reach the height calculated in Part B. Explain the main reason why the car does not reach this height. So not all of the energy at the start transfers to gravitational potential stores due to friction causing transfer to thermal stores. So that's our 2 marks. One for saying not all of the energy is transferred to GPE, and the second mark is explaining that due to friction some of that energy is transferred to thermal stores. Or we can talk about the work has to be done against resistive forces, which is again acknowledging the fact that there is friction. Okay, part 2. The car reaches point C, which is at a height of 140 meters above A. Calculate the speed that the car would reach when it descends from rest at C to its original height from the ground at D, if 87% of its energy at C is converted to kinetic energy. So let's take 0.87 of its GPE that it has at the height of 140 meters. So 8,300 times 9.81 times 140 is its GPE, times 0.87 gives us 87% of that. That then becomes the kinetic energy. So we've got a kinetic energy of 9917321 joules equals half mv squared equals 0.5 times 8,300 times v squared. Rearrange and square root to find v. We get a v equals 48.88, or 49 meters per second. So 1 mark there is for the calculating the 87% value of mgh, and the second mark is for the final value of the speed. And so if you've got that's the end of the run through the mechanics questions. If you've got the workbook, you've got the mark scheme here, and you can refer to that as well as watching the video. So thank you for watching.